Okay, yeah. So let's start the exercises. I do feel like I left out quite a bit of the theory portion, like, made it incomplete or something. But yeah, I think the proofs were easy, so you should be able to do them. And I wanted to focus on the intuition, right? How do you get to those proofs? So the main, what the thought required to arrive, the thought that's required to arrive at the solution, that's coming from the intuition. And for that, you need models of how the neighborhood works, how each neighborhood works, how each basis element looks like. So yeah, the picture is that picture is more important, I would say, than anything else. So once that picture is really clear, and the picture will become even clearer with these exercises. So you clarify that, that's far more useful for these problems. So yeah, the mechanical proofs, they start to become too obvious now, and that's what section, we dealt with all those mechanics in section 13, right? So yeah. Okay. I won't be attempting all these problems in order, so I'll just tell you the order right away. Let's see. So 1, 2, 3 should be in order. Yeah, 1, 2, 3 is in order. I'll attempt 4 later. I'll attempt 6 first. So 1, 2, 3, 6. Yeah, then 7, then 4 and 5. And then I'll attempt 9 and 10, and then 8, and then 11. So that's because question 8 refers to the exercises later, and question 11 is fine. Question 4, so my solution requires some mentions of what the uniform matrix open set looks like. So question 6, that's what it tackles. So because of that, we're going to do question 6 before 4 and 5. And 7 is just because it fits better. So yeah. Okay. So let's start with question 1. Okay. So yeah. So I'll sketch it first and then I'll show why it works out. Yeah. So what these elements look like, the sum being constant elements. So you have to look at how this would look like, right? X1 minus Y1 plus X2 minus Y2, all less than epsilon, right? So epsilon is the fixed value here. And at the extreme values where one of them is 0, it's going to be the entire thing, right? So at the positive and the negative, it's going to be the extreme thing. And yeah, so I'll sketch it first and then I'll prove it later. So it's actually a square but rotated. And that's because you take any point here, it's essentially this thing, because it's 45 degrees. And why would it be 45 degrees? Let's see. Yeah, so it's a square essentially. It's a rotated square. And the reason for that is because, let's see. Yeah, because these two are equal. So these two are equal. They're both epsilon. And because of that, it's going to be exactly 45 degrees, right? And because of that, this length and this length are equal. So what does that mean? That means along the path of the right triangle, it's going to stay constant. So the interior of this diagonal rhomb, it's a square, so also a rhombus, is what the neighborhood actually looks like. Neighborhood, balls, faces, and then yeah. So yeah, that's what it looks like. And this also gives us the same usual topology, and that's because, well, for every such square, we have this circle, right? So the same point here, but instead of, so what would this look like? It would look like essentially, so here is root 2 of epsilon, but in general, it would be epsilon by root n, right? So that would be lesser than the square here. It would be contained in it. And geometrically, the whole circle would be, there would be a circle containing it, and that's the epsilon circle. And the same thing here if you take the square metric, right? This is the regular square metric. So because you can always shrink it or contract it, they generate the same topology. And this is also more intuitive from the equivalent metric space definition I gave. So two equivalent metric spaces give the same topology. That's why they're called equivalent. That's the motivation of the definition. So yeah, so I sketched it in the general dimension. You'll have to, so it would look like a rotated cube and yeah, so on. And the point is you can shrink it. And this is more of a geometry problem. If you want another proof, essentially, yeah. So essentially the supremum of them times n times the dimension, right? So that would be more than their sum. So that's guaranteed. And their supremum, so the maximum among them all, times nothing is going to be less than their sum because less than or equal to because they're guaranteed to be positive. So the square metric is less than the square metric is going to be, hang on, sorry. Yeah, so the square metric basis is finer than them and coarser than them simultaneously. So if you want to write a proof, that's how you go with it. The square metric is, so I just said everything. You can write the proof on your own. It's just, but yeah, the square metric, that's all there is to it. So yeah, how do you write it more generally? So observe that the Euclidean norm is simply P is equal to 2, right? And yeah, they're pretty much circles. That's all there is to it. And the square metric is actually what you'd come closest to if P goes to infinity. So an intuition for that would be, well, let's see. So we have a bunch of terms, right? Actually, I'm going to write actual numbers here. So 8 plus 1 plus 2 plus 9 plus 9.5. So you raise them all to the power of a very high number, right? And then you take it that same very high numbers as root. So to the power a, a, 1 by a, right? So what's going to happen is the difference between 9.5, which is the biggest, and everything else will magnify by a huge amount, right? And essentially the difference goes to zero as a goes to infinity, and what remains is 9.5. So yeah, try to find the limit as a approaches infinity here. It's going to be 9.5, right? And yeah, that's the motivation for calling the L infinity norm, or there are many names for it. But the square metric is what happens as p approaches infinity. So for all p, you're going to get yeah, the same topology, the standard topology, because the square and the square are all contained in it. So yeah, you can have a square this way as well, right? So you can always have a square contained in it and outside. Yeah. So that's the geometric picture. Do I want to? Yeah. So you can write the formal argument in the same way. The supremum is going to be greater than them if you multiply it by the dimension, which is n here, whatever, and it's going to be lesser than them if you take a certain constant, maybe 1 by n. So because of that, they're going to be equivalent metric spaces, and it's the same thing. And of course, I'm assuming it's a metric here. To show that, you need the Holder inequality, which I think is discussed in section 21, aka the next one. So yeah, show that R cross R in the dictionary order is metrizable. So I'm going to come up with the metric first, and then from that, we just have to show it induces the same topology, right? So it should be pretty simple. Yeah. So for all x, should I how should I call it? Yeah, x belonging to R cross R. So I'm going to call it equal to A cross B, right? Yeah. So we're calling the basis elements around it as follows. Yeah. So how does the dictionary order go? It goes downwards or upwards? Hang on. Upwards, right? Yeah. So A till that way. Yeah. And it goes along the first coordinate. So the x coordinate stays constant and the y coordinate changes, right? Yeah. So it would be equal to A essentially A cross B minus, how do I write it? Hang on. So I could write it as an open interval. Yeah, fine. I'll write it. So this is an open interval, right? From A cross B minus epsilon to A plus B, A cross B plus epsilon, right? So yeah, now we need to show it's a basis for the usual topology, right? So first note that they're all consisting of open sets. So all we need to show is that these are contained, any open set in the dictionary order topology, the basis elements are contained in them. And that's true because you take any x in R cross R, you have a basis of epsilon, you have a basis element around it, right? So you choose that basis element, and then for that basis element, due to the density of real numbers, you can always find such an epsilon. So yeah, I'm using theorem 13.2 here, the basis for the topology one. So yeah, it's metrizable. Oh wait, sorry, one second. It's a bounded metric. So this is the basis elements, but what's the metric here, right? The metric is bounded here, x comma y. It's going to be the difference across the y-axis if the coordinates in the x-axis are the same, and it's going to be one otherwise, right? And so it's a minimum of dx comma y comma 1. So it's 1 if it's more than 1, that's fine. And if this is defined as the difference across the y coordinate if it's the same point, and 1 otherwise. Or infinity, you'll get 1 either way. Because, if you go across to the next row, there are infinitely many, continuum many real numbers in between. From here till, yeah, you have to cross the real line in continuum many times. That's what we explored in the ordered square. So things are being brought up again. Yeah. I don't know in how much depth to cover all of these, so it gets a bit hard. But yeah, it's a matter of how detailed to go through it. And I haven't exactly slept that well, so oh well. Yeah, so that's the metric, and the basis elements look exactly as I said, and yeah, they form the basis for the dictionary article. Okay, show that the metric is continuous. So I did spend too long on this. This was the first question I spent too long on. Question 8 was the other one, and yeah, showing it's continuous is actually quite simple. So what would an open set in R look like, right? So yeah, okay, if it's so A comma B, right? So if it doesn't contain 0, right, then it would either be completely in the positive side or completely in the negative side. If it's completely in the negative side, the inverse image is going to be 5. So the inverse image is 5, which is an open set, so we're done. So yeah, then there are two cases. It contains 0 and it doesn't contain 0 and it's in the positive side, right? Okay. So first I'd like to show that the basis element x, this thing, yeah, its closure is equal to the set of y such that d of x comma y is less than equal to epsilon, right? And I'm going to call this as c of x comma epsilon, right? So it's a closed ball essentially. And I'll also like to show that the boundary of such these things is equal to the set of y such that d of x comma y is equal to epsilon, right? In fact, that's exactly how I'm going to show it. Yeah, kind of. So how do I show that this is closed, right? Uh-huh. So you take a y, yeah, let's see. So this is a new problem, but essentially it's an application of the problem in question 17. So and we discussed the boundary in question 17, so let's discuss it further. So how do we show that every point here is a boundary point, right? So you take a neighborhood around it. Let's see. Yeah. So the abstraction device says it should be a boundary point, right? It's intersecting the complement as well as the ball and side. But how do you prove it? So any yeah, so any point that hmm, let's see. Okay, so z d of x z comma y is going to be let's see less than delta, more than zero for any such point in a neighborhood around the boundary point, right? So okay, yeah, this is an open set, so its interior is going to be the same thing, and the boundary union the interior gives the closure of the open ball, the yeah open ball. So that's exactly the theorem I'm using here. And I know this looks like a completely different question, but this is going to make our work a lot easier for showing the density. And it's better to have this theorem down anyways. So yeah, so we have this, and yeah, essentially, hmm. So this point z, d of x comma z, right, is less than equal to d of x comma y plus d of uh, z comma y, right? Yeah. So what does that mean? That means, hmm, okay. I think there's a better way to show it. So I won't think. I think I can do it right here, but okay. So this is definitely not in the interior, right? And I just have to show that intersecting this neighborhood, right? So then it belongs to the closure. Okay. Hmm. Okay, so there exists a neighborhood that's completely disjoint from, sorry, not disjoint, it's completely contained in that, in Y. Now, yeah, so it contains all of them, but I don't know. Show it. Oh, well. Okay, I'll think harder, I guess. Wait. Yeah, so it was actually a lot simpler than I thought. All you need to show is that this is closed, right? Then the fact that this is a boundary point will follow instantly because it's a part of the closure, right? Maybe I'll get to that, but it's not okay. It's yeah, it has to belong to the closure, so I'll get to that, and it's also and it's a part of the closure, and it's not a part of the interior, aka the open set. So that will show that it's a boundary point instantly. Okay. So first of all, if I show that this thing's complement is open, then yeah, we get another open set, right? Yeah. Hmm. So okay, yeah, we just have to show that anything that doesn't belong here, so y such that d of x comma y is greater than epsilon is not a limit point, right? So how do you show that? That's pretty simple. Here's the picture. So we have a ball here and we have any point outside. So we'll be able to draw a circle. And the fact that we can draw a circle around it or a neighborhood or basis implies that it's not a limit point to theorem 17.5. So how do we get such a basis? Quite simple. So since d of x comma y is greater than epsilon, this is a positive number, d of x comma y minus epsilon, right? So there exists a basis of that size around it, and it won't be intersecting even the closure because Yeah, because otherwise the triangle inequality will be violated. So how do we know that? Let's see. Let any z belong here, right? So d of y comma z is less than d of, yeah, I should reserve something. So I'll get to the boundary point soon. Yeah, is less than d of x comma y minus epsilon, right? Yeah. Now we are concerned about d of x comma z, and you have to show it's less than epsilon, right? So it's less than equal to d of y comma z plus d of x comma y. But this is greater than epsilon, and this is, so I just want to, yeah, something else. I'll flip it around. Hang on. So this is y, this is going to be x, and this is going to be z. Yeah, y, x, z. Sorry, y. Yeah, should be fine. Yeah, it's fine. So yeah, triangle inequalities do get a bit messy, but they help you prove a lot. So this is where the real fun in analysis comes in. So if you enjoy these, yeah, you like analysis. If you don't enjoy these, I'm not sure if you'll even like topologies. Yeah. So anyways, this is, yeah, I think it directly comes in now. Yeah. So you can just substitute it here. So this is, yeah, d of x comma y is greater than, yeah, some substitution has to be made now. Hang on. How do we make the substitution? Yeah, I can't believe it, but I'll take a break to think about this. Yeah, so I thought harder about it, and yeah, I'm done with this. But disclaimer: this is a fool's errand kind of, and does not help you solve the question at all. So I was just interested in a problem and I started it. Anyways, yeah. So the triangle inequality is slightly messed up. So we're almost there. It's not a major problem, but yeah, yeah. Y comma z. So here we're almost done now. D of x comma y minus d of y comma z is greater than epsilon, right? So I'm just going to write it here. And this is precisely what we need. So yeah, this would lie in the complement essentially. So it's an interior point is the point, and yeah, this is kind of the definition of an interior point, and precisely because of this, its complement is open. So because of that, yeah, this is closed. So the boundary point doesn't actually make sense because the boundary can very well be empty. So an example of this is the discrete metric. So I'll just show it to you. And the discrete metric does give you the discrete topology, so it's exactly what you think it is. I'll just give you an example of that, and that will show you why the boundary can be empty, so it doesn't make sense sometimes. In R2, it certainly does make sense, but there are some properties that are nice that allow us to go with it. And Hausdorff is not one of them because the discrete metric is also Hausdorff. So yeah, maybe it's locally compact. I don't know. Anyway, so yeah, no, locally compact also. Anyways, so the discrete metric is d of x comma y is equal to 1 if y is not equal to x, and 0 if y is equal to x. That's it. And this follows the triangle inequality because if the 2 points are not equal, then one is less than equal to 1 plus 0 or 1 plus 1, and yeah, 0 is less than. So it works out. So yeah, this is the discrete metric, and it gives you the discrete topology. So single point sets are essentially open because you take a ball of x of radius half, you get exactly that. And you take the points of the points that are exactly half distance away from x, there is no such point. And if you take exactly one, you'll get everything but x, and that's also technically a closed set. So yeah, so it was a fool's errand. Yeah. Now coming on to the question, we actually needed none of this. I realized I did have the solution. I just forgot how it works. So I was thinking that for the last case, we'll use this as the difference of an open set and a closed set, right? So this is, let's say this is zero, right? Yeah. So as you can see, the open interval that contains any open interval that doesn't contain zero is the difference of an open interval that does contain zero and zero till the endpoint. And this would be the difference between an open set and a closed set, and we've proven that this is an open set. And then I was going to prove that inverse image is open, but all of this was useless. But yeah, this is why I wanted to show that that's a closed set. So that would have done something, but not really. So this is how you actually do it. For all x in x, for all v of f of x. So in this case, d of x, I just write this, yeah, v of d of x bar. Yeah, yeah. Uh, there exists what basis? Yeah, u of x such that f d of u is contained in V. So this is the continuity criteria, the fourth one, which is the most important. Yes. Now, how do we use this? So let's say we have an open interval. So again, just like that, if it's less than zero, we don't care. If it's containing zero, then it ends up being something like closed interval 0, comma c, right? So we'll deal with this case too, but let's deal with this case. Yeah, let's actually deal with this case first, the 0, comma c one. So here, yeah. So we have a basis element 0, comma epsilon that's contained here, right? So yeah, the basis is actually open and it contains zero, but again the inverse image is pi, so we don't really care. Now, yeah, so we have the point x, right? So it's essentially an ordered pair x comma y, and it has some distance, right? Okay, so we have a neighborhood and we're taking the inverse. So if it's of this form, we're going to get essentially a ball around both of them, right? Yeah. And here, is that it? Let's see. Yeah, so slight mistake. Yeah, we don't have two cases of these two kinds. Also, yeah, I worked a bit. Yeah. So what we actually have is, so yeah, for any ordered pair, they may or may not be equal, right? So it could be x comma x or x comma something else, right? So if it's the same point, yeah, essentially f of x vector will be zero, right? And any neighborhood around it would be of the form 0, comma epsilon essentially, because uh, behind that there is the inverse image is empty. So sure, you could include it, but it doesn't matter. Yeah, so any neighborhood you have of this will have 0, comma epsilon as a basis, and the inverse image here would translate to a basis essentially. So yeah, it's going to be open because, oh yeah, sorry, yeah. So for this case, we can just take a smaller epsilon essentially. So a neighborhood of exactly epsilon, radius exactly epsilon or epsilon by 2, and its in image set would be contained in 0, comma epsilon. So we got an image set that's contained, and that's what we needed. So yeah, that's the proof for continuity for this case. And if there are two different points, then it's f of x would be something, some positive constant, let's say d, and Yeah, so C, right? And yeah, so we have for any open set that contains this, we'll have some basis elements. So let's say D minus epsilon and plus epsilon, right? So an epsilon neighborhood around it. And yeah, so you just take epsilon by 4 or 120 to be safe, and you take a neighborhood around these two. So now you check the distance between any 2 points here, and what would happen is it would be contained here, and that's because its distance to any point would be so its distance between this point and let's see, I'll draw it bigger, but the triangle inequality argument holds the same. So for any point lying in the neighborhood epsilon by 120, its distance to the center will be less than or equal to d plus epsilon by 120, right? And you take any other point, you just have to add another epsilon to it, epsilon by 120. So it will be epsilon by 60 plus d, and that's going to be the like range of error, right? You can prove both ways. You might have to, yeah, but that's how the triangle inequality works. So you have to prove a greater than and a lesser than inequality to show that it actually lies in the range. It's yeah, but that is the way to do it. So yeah, okay. Now to show, so yeah, I spent 4 hours on the B part and I still didn't get it right. I think I finally figured out the solution just now. So let's hope it's correct. Yeah, so I'll consider the subspace topology for any arbitrary point x. So x naught cross x, and we can restrict the function d from here to r as follows. So we have essentially d of x naught comma y, right, and y is in here. So it's essentially a function defined on a single variable now, right? And the point here is that the inverse images are going to give us open sets in this coordinate. So we're just going to get a single point here for any neighborhood of x naught. So we don't really care about the subspace topology, but here we're going to get the open sets, and we're going to get capture all those open sets through the inverse images. So yeah. Now note that in any order topology, d of so the function being actually, yeah, we did prove this. So d of x naught comma y less than epsilon is an open set. We showed this in the order. I think it was closed sets or Hausdorff. Yeah, section 17. I'm not sure. We proved it. F of x is greater than g of x. So g of x can be taken as a constant function, and that's an open set, right? So that's also an open set. So we showed that, and using that, and yeah, you just take the inverse image, you'll get a basis element. Right, you take the inverse image of the set, you will get the set of all y such that this is the case, which is exactly what the basis element is. And since the inverse images must be open, uh, so it's going to be x naught cross any inverse image here, right? And the inverse image here will essentially be this. So what do we get now? Since every open set containing x, which is a subset of x naught cross x, it must be a product of an open set cross an open set on X. It's yeah. Essentially, I'm using the definition of the Cartesian products open sets. The definition of the open sets there, and we also have a basis there. And yeah, from the inverse image from of D here, it's going to be of the form x naught cross b, x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 x 0 And this is by definition an open set since P has to be continuous, and therefore every basis element is contained here for all x naught. So the x naught is arbitrary here. Yeah. So yes, I'm okay. I'm pretty sure this argument is correct because I'm using the inverse image property correctly here, and this is an open set because we've shown it in an order topology. So yeah, this should work. Okay, so I think I said I'll do question 6 and 7, right? Yeah. So question 6, yeah, show that u epsilon is not equal to the ball here. Yeah. So this uh, is what? This is the set of all sequences such that, hang on. Yeah, the uniform metric is less than, yeah. So supremum of xi minus yi is less than epsilon, right? So I'll give an example of a sequence that lies in u x epsilon, right? So I'll call it y, I guess. That doesn't lie here. And it's a very simple example. You just take x plus xi plus epsilon minus 1 by I. There you go. So what's going to happen here? The supremum of xi minus yi is essentially going to be epsilon minus 1 by i's supremum. And what is this? This is exactly epsilon, not listening. So yeah, it kind of acts as a boundary, solid barrier, spoilers for rain world, like, yeah, so it's like that kind of barrier. So, and that barrier actually consists of limit points, and I'm going to show you that. So before I show you that, to define the limit points, I'm going to have to elaborate on what the open neighborhoods look like, right? And for that, I'll attempt C part. So C part first, then P part, right? Yeah. So C part is far easier to show. So first, I just have to show for any arbitrary delta less than epsilon, u x delta belongs to is contained in B rho x epsilon, right? So if, yeah, so if we're taking the set, the supremum is going to be less than or equal to supremum of xi minus yi is going to be less than or equal to delta, which is less than epsilon, so we're fine, right? And for the other way around, supremum of xi minus yi is less than epsilon, so let's take it to be equal to delta, and yeah, it's definitely going to lie in ux comma epsilon plus delta by 2. And we've shown that this in section 4 that this is less than epsilon and greater than delta, since delta is between the two. This is between the two, right? With since delta is less than epsilon. So yeah, so any member here is contained in the union, right? So C part was easier to show. So now that we have shown that, I'll show why the example I gave, the 1 minus epsilon minus 1 by I1, that is why that is yeah. So now that we have attempted C part, it's quite easy to show that the sequence I gave. So what was it? X bar xi what plus epsilon minus 1 by I, right? Yeah. So this is not in the neighborhood, right? We've shown that it's not in the, yeah, it's not equal to the open ball. So that's why, yeah, we showed that. And it does belong to u, so it belongs to u x comma epsilon. Now, if I show that this belongs to limit point of v rho of, right, so it doesn't belong to It doesn't belong to the open set itself, but it belongs to its limit point, set of limit points. What does that mean? That means that this isn't open, right? Since it contains this, but it also contains its limit point, and it doesn't belong to this. Yeah. Just let me clarify things clearly. Yeah. Yeah. So one small correction. I'm not going to show it's a limit point of this. I'm going to show it's a limit point of this thing's complement, right? So essentially, it's going to intersect its complement at no matter what neighborhood you take. So let's take neighborhood B rho y bar epsilon prime just to be safe. Yeah, and this. So there's going to be a u y delta contained in it, right? Okay. Now, because of that, it's going to intersect the complement at least one point, and that point can be, let's see. So there exists an I such that if it's large enough, it's going to be smaller than this delta, right? And yeah, so then it simply must. Okay, so what's going to happen? So the delta band is essentially going to go outside, and why is that? It's going to go outside in the sense of, yeah, if delta prime is greater than one by I, then we're going to exceed epsilon, right? Which is exactly the complement, and it's going to lie inside of this set. So a neighborhood contains this, and here we're going to find a point, a sequence that lies beyond this epsilon boundary, according to this definition, and that precisely means it's a limit point of the complement, right? So I hope the argument works. Like essentially, yeah. So because of one by I being decreasing, there exists an I such that delta prime is greater than 1 by I. So you just choose that I, and from that point onwards, you're kind of you have an infinite choice. You always have a choice of points that are lying outside the epsilon boundary, and you can and this neighborhood is actually intersecting with them. Yeah, this neighborhood. Okay. So what have we proved just now? We have proved that this sequence lies in the complement's limit point. It's a limit point of the complement. And since it already belongs in U epsilon, I'm just going to call it that, it's a boundary point. And no open set can contain a boundary point. So yeah, we've proven that. So I'm not sure why I went for this method, but this is definitely a method, and yeah, that's why I wanted to attempt C part first. Okay, so let's attempt question 7 now. So I was a bit naive with thinking that the box and product topology are easily homeomorphisms. They are homeomorphisms, but you definitely have to be careful because if you go from product to box or box to product or uniform to product, and there are six, two and two, right? So no, there are nine possibilities, right? Yeah. So you have a lot of options, and not all of them are homomorphisms. Thankfully, the question only asks us to talk about uniform to uniform, right? So yeah, and that's pretty simple. So yeah, let's say you have a uniform, basis element here, rho epsilon, right? So a basis element is an open set, right? Now, if we can design a function such that the continuity condition is violated, so f of u is not contained in that no matter what epsilon you take, then yeah, you've gotten a discontinuous function. And one example of such a function is an increasing. So AI is increasing. So how would that look like? So let AI is equal to I, right? So it's increasing, and what would happen is the neighborhoods would also expand, right? And so how do I explain this? Let's say we have B. So this is f of x, right? F of x bar, yeah, and this is x bar, right? So B x bar delta. The delta at the ith coordinate will become I delta, and at some point it must be bigger than epsilon. So if AI is not bounded, then we will run into a problem. So that's how you ensure continuity. So AI must be less than equal to m for all I. Note that the constants don't matter. You just shift them around. It doesn't really make a difference. But yeah, so if AIs are bounded, then the forward function is continuous. Now, for the backward function being continuous, you can just check, for the inverse. You can actually check the inverse function itself because it's a bijection, so you can create it. And this one is easy to make too. So it's going to be something like this, right? And yeah, essentially, you need 1 by AI to be bounded. That's pretty much it. So if AI is bounded, so all the constants, all the multipliers are bounded, then you can just take epsilon by or delta by m, and that's right, epsilon. Yeah, so epsilon by m, it's going to stay within the bounds. But yeah, you need these conditions. So it also can't be converging to zero. If it converges to zero, then you approach something like a constant function, and the inverse image of a constant function is just the entirety of R. So yeah, you'll approach something too big, and because of that, it won't be a homeomorphic. But yeah, if it's roughly constant, then it's going to stay one. And yeah, the box topology doesn't have such problems because it's fine enough that you can have more open sets to play around. And the product topology doesn't mess around too much because it has too few open sets to mess around. So yeah, it's quite nice. I thought I actually, on seeing this question, I thought I did the previous question incorrectly, but no, I think I'm still, yeah, they still very much are homeomorphisms. It's just that this one has a condition on it. Of course, note that AI has to be greater than zero, so we can't have constant functions. So, yeah, I was thinking of those cases too. But yes, this serves as a great motivation behind solving question 4 and 5 now, which is why I wanted to do these first. Yeah, so question 4. So yeah, we just have to show whether some are continuous. So the reason of that criteria can show you why the first one isn't continuous for the uniform support, right? Yeah. But it is continuous for is it continuous for no, it's not continuous for the box topology because you can have that nonsense again, right? The nonsense, that's the example. So we have an open set of the form, x bar, xi minus 1 by n, 1 by I, comma, xi plus 1 by n, right? And you can have as much of a shrinking function as you want across the series. So yeah, think of these topologies as series essentially. And the uniform topologies are bands. The product topologies are finite. You can do whatever you want, but in a finite space. And the box topologies are, yeah, you can do whatever you want. And the box topology is the freest. Yeah, I'll just be back. Okay, so before I go any further, I'll just state a lemma that if we have a function from x to y1, comma y2, comma y3, and it's in order of coarseness, so y1 is coarser than y2 is coarser than y3, right? Or finer, whatever. Then if some function is continuous here, then it's going to be continuous in all of them, right? And if some function is discontinuous here, it's going to be discontinuous in all. I hope I got it right. So essentially, if some function is discontinuous in the uniform topology, since the box topology is what finer, we have more open sets to check from, and the box topology also has those. And what ends up happening is, yeah, the inverse image of an open set from the box topology is not open, right? So essentially, check for the product first. If it's continuous, then check for the uniform, and then check for the box. And since the uniform topology is discontinuous, the box topology is also automatically discontinuous. So yeah, no need to check further. For the second one, the box topology is already shown as discontinuous by the example, and it is continuous. I believe is it continuous in the uniform topology? So I think it should be. See. Yeah, so it's actually satisfying the criteria I mentioned in question 7. So yeah, and it's also continuous in so the uniform topology is continuous, and therefore so is the product topology. It does go both ways, yeah. So because it's continuous in the uniform topology. So yeah, and if you want to be efficient at it, check the uniform topology first, because if it's not continuous, then neither is the box one, and if it is continuous, then the product one is automatically continuous. Then you just have to take the box. And the box topology is not okay. So the uniform topology is continuous on the third one, right? Because the decreasing sequence doesn't matter; it just has to be bounded. Okay. So what's remaining is the box topology on the third one, and that's discontinuous, and I'll show you why. Yeah, you just take a tick. Let's see. So what was the neighborhood chosen? Hang on. What's the example? Or is it not here? Hang on. Oh, it's in the product topology, isn't it? Yeah. So the example is in the product topology section, right? Yeah. Okay. Yeah. So if we have a delta, then the example given in the product topology section would be at least for that open set, we do have one delta that it works out for, but we don't have one for. So essentially, this is how fast it's shrinking, right? So if it's 1/2, then 1/2, and so on. The function that's shrinking only by 1/n, it won't be shrinking fast enough to be contained in all the neighborhoods. And yeah, so that's precisely why it's not going to be continuous in the box topology. You find any decreasing function, I'm going to find a smaller one for that than that. And since the box topology gives me full freedom, I'm just yeah, it will eventually escape it. So yeah, look at the scale factors as shrinking the errors, and if the error is too large, then it stops being continuous. You can think of that, and think of the neighborhood as errors, right? So it just blows up or shrinks. Okay, so in which topologies do the following sequences converge? Okay, so note that all three topologies are actually Hausdorff. So any metrizable topology is Hausdorff. We'll prove that later. But the box and product topologies are Hausdorff, and yeah, we just need to show it for the uniform one. But again, it's metrizable, so we're done. So all three topologies are Hausdorff, and because of that, they're only going to converge to 1 point if they converge at one. So we just need to rule that one out. Then we're done. Yeah. So for the first one, all candidates would be of the form, n going on till infinity, right? These are all the possible candidates could converge. But note that all these candidates have a neighborhood in the product topology itself that, hang on, is it converging in the product topology? Probably not. Let me just think about it. Okay, so before I go any further, I'll just state a small lemma or whatever. So since the box topology is finer than the uniform topology, which is finer than the product topology, we've proven this. If something happens to converge in the box topology, then it automatically converges everywhere, right? Because we have more fewer open sets to choose from, and we need to check for each of those open sets. So most of the time, I'm going to check for the uniform topology. If it doesn't converge, then we have to check for the product one. If it does converge, then we have to check for the box one, just like the continuity one. So yeah, okay. So the that sequence does converge in the product topology, and it doesn't converge in the uniform topology. So I'll first explore the uniform topology case. Yeah. So all candidates will look like of this form, right? And yeah. So if it's any integer, you can essentially get a what half difference band and just work with that. So and then we have half epsilon being half band around it, and it's essentially intersecting none of the sets. And you can check that for all of the candidates. So the only remaining candidate is all zeros, right? So yeah, let's check that one out. So all zeros. So if we have some epsilon band around it, what would happen? Um, yeah, it would intersect none of them. So if we take the half band around it, just like earlier, so half and half, and yeah, the half band would essentially translate to exactly what is discussed in question 6. So I'm talking about row zero vector half, essentially. This is the row. Yeah. So that's what I mean by half band, essentially. So we already discussed what they look like, and that's why I wanted to solve question 6 first. And because of that, I can just use them quite casually. Okay. Yeah. So this is actually intersecting none of them. So all candidates have been ruled out, right? It may match them at finite coordinates, but it has to match them at every coordinate to intersect them, right? The neighborhood has to contain a point that is lying in it for every coordinate. And with the half radius, none of that happens. So yeah. Now in the product topology, it is interesting, and yeah, that's where. So the product topology is analogous to all but finite, and note that all tails are also analogous to all but finite, right? So yeah, essentially you take the infinite tail and then you take its complement, you're going to get a finite body, I guess. Yeah, and that's what. So if we study that, we're automatically studying the product topology because they're both contained in there. Every finite complement is going to be the product topology, and every tail contains that. So yeah, every body is a product, is a finite product, and every tail contains that finite product. So they're both kind of equivalent. Anyway, so the product topology does actually converge. In the product topology, it does converge to this point. So let's go further. Why is that? So yeah, let's say the product topology has open sets till, let's say, n, right? So until n, it doesn't need to intersect any of the sets. But what happens after that is it's going to be zero until zero and intersecting at every set. And afterwards, it's going to be the entirety of R. And because it's the entirety of R, it's going to intersect every set from so on, from n onwards. So just to give you an example, if n happens to be 50, you get zero till the 50th point and then R's from that point onwards. Sorry, not zero. You're going to get a neighborhood of zero and then R's from that point onwards for the product of both. And yeah, we intersect. So the neighborhood is going to have intersect a point of zero, which is going to happen from 50 onwards in the sequence. And after that is going to be R. So it doesn't matter what the points are. So you can generalize it to a point that increases in zeros like that. That also works. So the actual nature of the sequence doesn't matter for the product. But for the other ones, it's not converging either. Yeah. Okay. Let's check the uniform topology for the second one. So X1 and that. So it's all ones first, then zero, I believe. Yeah. Zero, half, and so on. 0, comma 0, and then one third, and so on. Yeah. So it is actually converging to the point, and yeah, we discussed uniqueness already. So it is converging to the point all zeros, and that's because you take any epsilon band around it. So any epsilon band, right? There has to be some 1 by n that's less than epsilon, right? And from that point onwards, from that n onwards, what's going to happen is the all of the sequences are going to lie inside the band. So yeah. So now we just have to check for the box topology. And for the box topology, it once again does not converge, and that's because, let's see, so how do I design a open set that avoids all of it? Yeah, so we have a neighborhood around zero. Yeah, let's see, half. Yeah, so since it's the box topology, it need not be consistent over the whole range, right? It can just be any value at any point, any coordinate, I mean. So let it be, so 0 plus minus half 1 by 2i. Yeah, okay, this is a bad notation, but yeah. So the 0 doesn't matter, but I'm just writing it for presentation, and yeah. This is an open set that actually avoids all the points of the sequence. So we have an open set that avoids all the points and therefore all but finitely many too. So yeah, it doesn't converge in the box topology. And of course, it automatically converges in the product topology because it converges in the uniform topology. So yeah, the next one is similar, I think. Let's see. Yeah, so you can make a box topology avoider as well. So that same set works out for y as well, and for the, let's see, for the uniform topology, it's the same logic. It's the exact same principle. There's nothing different, anything different here. Yeah. So it converges in the uniform and the product topology and not the box plot. Now Z is the only sequence that converges in the box topology as well, and therefore all three of them. And that's because whatever neighborhood you take around the point 0 in the first two coordinates, it's going to whatever epsilon you take, there's going to be an n that's less than it. And the point is, actually, it doesn't matter if it's a 2, it can even be finite. So if it's finite, you take an epsilon, you take the minimum of them all. You don't need to take. Yeah, just take the epsilon, and all of them are going to converge eventually. So yeah, the point is the epsilon cannot go too small, and we are exploiting that finiteness precisely to show that it converges to 0. So yeah, epsilon band here, and then some 1 by n has to come there, and same thing on the other one. It can even be delta, doesn't matter. We'll take the minimum of it. And there has to be some n that crosses is less than the minimum of it. The 1 by n is less than the minimum. And it extends to finite coordinates. So yeah, this one, yeah, I was quite hesitant to solve back when I had to solve it. But yeah, thanks to making these videos, I feel like solving them more. So because I kind of have to, so it's a nice incentive. Thank you very much. Okay, so as promised, we're solving question 9 first before question 8. So let's do that. Okay. So we're assuming Rn a fixed dimension, right? And x, we have to show that x dot y plus z is equal to x dot y plus x dot z. And the dot product is exactly what you know in linear algebra, which is just the coordinate-wise multiplication and then summing them. So yeah, and a sum is just summing the coordinates individually. So let's see what each side is any nth coordinate is going to be. So it can be any mth coordinate, m less than or equal to I. So x m LHS. So yeah, x m dot ym plus zm. That's the definition, right? And through the distributive property of proven in section 4, it's equal to xm dot ym plus zm dot xm, doesn't matter, it's the same thing, right? So yeah, essentially the property transfers over because of the distributive property at each coordinate. So yeah, now let's show the other one. So what's x dot y, right? X dot y mod, the regular mod, I believe. Yeah, regular mod. This is the definition, right? What's the hint here? I'll just follow along the hint. Yeah. So A is equal to 1 by norm of x. So norm of x is, oh yeah, observe that norm of x is equal, square is equal to mod of x dot x. In fact, just x dot x is fine as well here. Yeah. Yeah. So no need for the mod here. So observe that this is the case, and this implies that norm of x is equal to square root of x dot x. Note that we're taking the positive square root by the notation and also by the definition. And of course, this implies that norm of x is positive no matter what, or non-negative at least. Yeah. So how do we handle ax plus minus dy as the question asks us to handle? Okay, so yeah, I just showed that for any arbitrary case it's non-negative. So this is nothing special, right? It's forming a closed field, I guess. How do I explain it? Let's see. Okay, essentially, whatever combination we take, it's still going to belong to us. So yeah. So now that we have this at our disposal, what do we do? So let's square it. Since it's positive or zero, its square is also going to be positive or zero, and this is equal to ax plus minus by dot ax plus minus by, right? So let's compute it. This is a square. Yeah, so this should be fine. And note that this is greater than equal to zero. I think we're almost done now. We just need the last step, which is, yeah. Hmm. So this is what we need, x dot y. And how do we handle the mod? Okay, so the solution of the problem is equivalent to showing that x dot y upon norm x dot norm y is less than equal to 0. Oh, sorry, 1. Right. Hmm. Okay, so since they are positive numbers, we can divide by a square b square. We have a square. Yeah, so I was being a slight idiot. So a couple of things. First of all, I didn't really use the properties properly, so I'll just rewrite it some things. Yeah. Okay, so yeah, so this is greater than equal to 0. That's completely fine, but just note that I'm actually using the distributive property twice here. We've expanded like that before, but it's actually a square dot times x dot x, which is actually equal to a square. So that's why it ends up being 1. Sorry, 1 by a square plus b square y dot y plus ab uh, x dot y plus ab y dot x. So these two have to be proven to be equal, and for that you just use the fact that you can switch these around. So so yeah. So these two are equal, and these two are essentially one each. So yeah, 1 plus 1 plus 2ab x dot y is greater than equal to 0 plus minus. Yeah. Okay. So now that we have that, we can yeah. So 2 is greater than equal to and less than equal to or something like that. Hang on. Yeah, it's greater than equal to minus 2 ab x dot y and greater than equal to plus 2 ab x dot y. And this directly implies that x dot y into ab is less than equal to 1. And from that we have x dot, sorry, mod, yeah. X dot y mod is upon norm x, norm y is less than equal to 1. And this directly implies the thing that we have. So yeah, the key thing I missed here was that this is x dot x, which is exactly equal to a square, 1 by a square. So yeah. Okay, now let's show the triangle inequality. This thing implies the triangle inequality very trivially. I'll show that as well. Yeah. Okay. Hmm. So now we have that x dot y is less than equal to norm x dot norm y. This is the regular multiplication. This is the dot defined here. Okay. So as the hint says, let's compute x plus y dot x plus x dot y. This it doesn't really matter. I've been using the notation quite inconsistently. Okay. So this is equal to norm x plus y whole square, and it's equal to x norm square plus y norm square plus 2, yeah, x dot y essentially, right? And now we get to use this inequality. This is greater than or equal to, no, less than or equal to, yeah, norm x plus norm y whole square. Yeah, I'm just using it directly. And then I'm using the a plus b whole square formula. And yeah, this directly implies what we want. So since all these numbers are positive. So yeah. So now that we have this, we just use the, let's see. So d of x comma y is precisely equal to norm x minus y, right? Okay. So yeah, and let's take d of y comma z to be norm y minus z, right? Yeah. So if we use the formula here, we get norm of x minus y plus y minus z. Yeah, norm is less than or equal to d of x comma y plus d of y comma z. And yeah, from this we directly get d of x comma z. And this proves the triangle inequality. And for the other two, let's see. So this one is norm, and essentially it's a positive number no matter what. So even if you multiply it by -1, you're fine. That's why symmetry applies. And for the first one, if this is zero, then norm of zero is by hang on, is it defined somewhere or yeah, I mean okay, so for the zero vector you just multiply a bunch of zeros. So you get 0 plus 0 plus 0 n times. So yeah, that's zero. Yeah, okay. Okay. Let's solve question 10 now. Okay, show that if x comma y belong to x, aka sigma xi converges, sigma xi square and sigma yi square converges, right? Not less than, yeah, less than. So if it's a constant, then it also has to, yeah. So let's see. Okay, so if these two converge, then let's see if we can show that these must converge. So yeah, so how do we show that this also converges? So okay, so first of all, let's prove that this converges. And this is easy to show. Let's see. Actually, no, sorry. We are, let's see. Okay, I'll think about it. Hang on.